Okay, section 10.4 is all about solving radical equations, and there are 5 boxes, so let's just dive right in. Box number 1 says solve the square root of x plus the number 7 equals 16. This one's pretty simple and straightforward in the sense that we're just going to subtract 7 from both sides. We would do the normal procedures that we would have, and we would get the square root of x is equal to 16 minus 7 is 9. So then from here, I am going to square both sides to undo that x underneath the radical, and I will get that x is now equal to 81. And then from here, I can check and see if I did this right. So the square root of 81 plus the number 7, is that equal to 16? Yeah, the square root of 81 is the number 9. 9 plus 7 is 16, and 16 is equal to 16, so I can verify that I did it correctly. Okay, box number 2 is similar, but this time we have a square root on both sides. So we have a radical on each side of the equation. So the first thing you're going to want to do here is you want to square both sides of this equation. And the square root of 5x minus 11 squared is just going to give us back 5x minus 11. And the square root of x plus 5 squared is just going to give us back an x plus 5. Now from here, we just solve it like we normally would. So I'll subtract x, I'll subtract x. So I get 4x minus 11 is equal to 5. I would add 11 to both sides, add 11 to both sides. So 4x is equal to 16, divide 4, and of course we get x equal to 4. It's always a good idea to check to make sure that we're doing this right. So if I take the square root of 20 minus 11, is it the square root of 9? So the square root of 9 equals the square root of 9. Check, I'm doing it correctly. Okay, in box number 3, I want to talk about this thing that's called the extraneous solution. So let's begin with a very, very basic example, and let's work forwards, and then let's see what happens when we look backwards. So let's say I've got x equals 3. If I square both sides, I would see that x squared is equal to 3 squared. So therefore, x squared is equal to the number 9. Well, this is going to produce for me, x could either be the number 3 or the number negative 3, and here's why. If I take the number 3 and I multiply it by 3, of course I get back a 9. And if I take the number negative 3 and multiply it by a negative 3, of course I get back the number 9. So there are 2 distinct different answers or solutions such that when I square them, I get back the same value of 9. Whenever you are squaring both sides of an equation, you have the opportunity to produce an extraneous solution, and we need to take that into consideration when we're solving radical equations. Okay, let me show you an example in box 4 where the extraneous solution is gonna show its face here. So I have x is equal to the square root of an x plus 12. Well, what you're gonna wanna do first is square both sides so that you can undo the stuff inside the radicand here. So remember, the square root of stuff squared is just the stuff. So you're going to get back whatever you have when you take the square root of something squared. So now I get this. X squared is now equal to an x plus 12. If I bring everything to one side, I get x squared minus x minus 12 is equal to 0. I would solve this using a diamond problem. Negative 12 and a negative 1. Probably a 3 and a 4. If the 4 was negative, they would add the negative 1 and multiply it to negative 12. So therefore, this is going to be the product of 2 binomials, x plus 3 and x minus 4. Using the zero product property, I would get x plus 3 equals 0 or x minus 4 equals 0. This would tell me that x has to either be negative 3 or x has to be 4. So I've got 2 very distinct answers, and I could have potentially created an extraneous solution because I am squaring it. So what you need to do is you must check. And here's how you check. You simply just plug in. Is negative 3, I check into the original, is negative 3 equal to the square root of negative 3 plus a 12? Is negative 3 equal to the square root of, well, 12 minus 3 is 9. Is negative 3 equal to 9? Or, excuse me, 3. Well, that does not appear to be true. What happens if I take the 4? Is 4 equal to the square root of a 4 plus 12? is 4 equal to the square root of 16? Yeah, a 4 is equal to a 4. That one I can justify. This one I cannot justify. Therefore, this answer is extraneous. And I'll just ext for extraneous. Okay, box number 5 is another interesting case where we have to consider. Let's say I have the square root of 3x plus 8 equals 2. Well, you would then say the square root of 3x is equal to 2 minus 8, which is negative 6. Then you would want to square both sides of this equation. And I would get 3x is equal to the negative 6 squared is the number 36. Dividing by 3, dividing by 3. 36 divided by 3. So x is going to give me a value of 12. Okay, let's go ahead and run this through and see what we get. Square root of 3 times 12 plus the number 8. Is that equal to 2? Well, 3 times 12 is 36. So the square root of 36 plus an 8, does that equal 2? Square root of 36 is the number 6, so 6 plus 8, does that equal 2? No, because this is equal to 14. So when does 14 ever equal 2? It doesn't. So just because you get a nice, easy, pretty number at the end doesn't necessarily mean you're going to get an answer to the equation. This equation has no solution, and here's the graph to prove it. If I do the square root of 3x plus an 8 and then y equals 2, there's no way that these two graphs are ever going to intersect. They have no points in common, no matter how far out I go for any x value. So therefore, it makes sense that I would get something that gives me a false statement. So the algebra supports that. Okay, hope that makes sense to you guys.